Hello again. This is our third video for Chapter 8. We are going to cover sections 9 through 12, which will cover reactions 6 through 10. Oh, went too far there. There we go. So we're going to start with reaction number 6. Again, we're starting with our alkene. This is our alkene chapter. So here's our alkene. And this is what we call a halogenation reaction. So we're reacting it with our halogen here. And underneath the arrow is CH2Cl2. This is methylene chloride. So it's a very common solvent to use. It gets used in the lab a lot as a strong cleaning. It's just a solvent in this case. And here's what we're making. We're going to add a halogen to each of our vinylic carbons. So our double bond carbons is going to bond to that to the halogen. And so this is a dibromide because it has two bromines in it. And we also use the word vicinal. Vicinal means that they are on neighboring carbons. So it's just for us to say where they are located. So saying that they're vicinal tells us about our regiochemistry of our structure. And then down here is giving us a little bit more information about our stereochemistry. So up here it's telling us that it is an anti-addition. So that means that our bromines are going to add from opposite sides. So in our ring, again, the ring helps us see the stereochemistry a little bit better. We have one bromine that adds to the top in a wedge and then to the bottom as a dash. And so we will get the pair of enantiomers in this reaction. So this is also what we call a stereospecific reaction. Look at the mechanism for this. It looks a little different, but we're going to see this type of pattern in a couple different reactions. So here's our first step. We're doing a nucleophilic attack. So again, our pi bond is acting as our nucleophile. We're attacking that bromine. But the bromine is also a nucleophile, so it's attacking that carbon. So right here we have this little circle of electrons that's happening, and our other bromine is breaking off, and so we have the loss of a leaving group happening right here. And so our intermediate has this 3-atom structure, and this is the same thing we saw with our mercury group in our last video. So in this step, our second bromine, so the bromine that broke off here became a bromide ion. Here's our bromide. It's going to do a nucleophilic attack on one of our carbons, and then our bromine carbon bond is going to break. And so what we end up with is a bromine at each of those carbon positions. Here's a little bit more to show us why it's stereospecific. So when we describe something as being stereospecific, that tells us that the stereochemistry of the products depends on the stereochemistry of the reactants. So for example, if we start with a cis double bond, we add our bromines in a dashed formation, and so we get these as our products. But if we have the trans form of the butene and we add the bromine in the addition, if we rotate around this middle bond here just for comparison purposes, we create this structure. So it shows us that starting with the cis or with trans double bond gives a different product. Now down here it's telling us that this is meso. So the reason why it's pointing that out is because if we were to draw this same thing but with a dash in this position and a wedge down here, it would mean they would act the same as each other. So even though they're mirror images, they are identical structures. So we are going to do a little practice problem. There we go. So we're going to start with what we just learned, as well as a reaction from our last video. And so we're going to look at this, reacting it with our halogen, with methylene chloride, and with our hydrogen with platinum. Now the reason that I want to show both of these is because our hydrogen addition and our bromine addition. And so when we add hydrogens onto our vinylic carbons in this structure, we're going to add them so that they are both in a wedge or both in a dash formation. So I have both of my methyls both of my methyls are in a wedge, and both of my hydrogens added from the back side in that dashed form. Now on my bromine reaction, on one side I'm going to have my bromine in the dashed position, and on the other side, I'm going to have my bromine in the wedge position. And for this one, we will also form the enantiomer. Made my wedge too big. Over here, this one is also meso, just like the example on the slide. Even though we would normally also form the enantiomer, for this one, the enantiomer is exactly the same thing. So let's move on to reaction number 7. Reaction number 7 is called a halo-hydron reaction. So the halo is telling us that we're using a halogen, and the hydron part is a reference to water. So that tells us that we're going to be reacting a halogen and a water molecule. So here's our alkene. We're reacting it with Br2, and for this reaction we can use bromine or chlorine or iodine. Let me add that up here. So we're going to say that X can be bromine or chlorine or iodine. And this is generally the rule. There are definitely exceptions to that, but that's for the most part the rule. So we're going to react this with our halogen, and we're going to react it with alcohol. Now we can also use I said alcohol, didn't I? We're going to react it with water. We can also use alcohols for this, and I'll show you how we do that in our example problem here in a couple slides. Regioselectivity, the halogen is going to go to the less substituted side, and the oxygen will go to the more substituted side. So here's our alkene. This would be our less substituted carbon. This is our more substituted carbon. So there's our halogen adding to that substituted side, and here's our alcohol adding to the more substituted side. Now, as a minor product, we will get the halogen adding to both of those positions, so going through reaction number 6. And then here's the same reaction, but with our chlorine. So here's our 2 carbons, and this would be our less substituted carbon. Here is our more substituted carbon, so our chlorine is adding to that less substituted side, and our alcohol is adding to the more substituted side. So we're going to look at our mechanism for this one, and it looks very similar to our last one. The first step is exactly the same, nucleophilic attack on our bromine, and then our bromine does a nucleophilic attack back on that carbon, and that second bromine is acting as a leaving group. So now we have that 3-atom intermediate, and here's where our water is going to come into play. We're going to do a nucleophilic attack from the water onto our more substituted carbon. So just like we saw with previous reactions, because this is an unstable bond, we want to react it with the side that would create a more stable pseudocarbocation. So that's what these pictures down here are telling us. The carbon that is more substituted is going to have a more stable partial positive charge, and so that's the bond that's going to start to break, which means that's where our oxygen will add. So this is what will happen. As this bond breaks, our bromine will still be attached to the carbon on the right, and now our oxygen is attached to the carbon on the left. And we've seen water used as a nucleophile before. We know when it adds, it goes from being neutral to being positive. So that last step that we need, we're going to use a second water molecule to do a proton transfer to get rid of that extra hydrogen so that we end up with our neutral nucleophile. So we've added our bromine on the less substituted carbon, and we've added our alcohol onto that more substituted carbon. All right, let's look at our next reaction. Reaction number 8 is called an anti-dihydroxylation. Or dihydroxylation would be a better pronunciation. So di is 2, hydroxyl, again, another word for an OH or an alcohol group. So it's telling us that we're going to add 2 alcohol groups and they're going to be anti to each other. So we have our alkene. We're going to react it with RCO3H. So this is definitely a generic version of our reagent. The R can be a lot of different options. This is called a peroxy acid though. So a peroxy acid has this CO3H group, so that's what this portion of that molecule is. So carbon to an oxygen, and then single bonded to an oxygen, and then there's an in there before we get to that hydrogen. This is a very common peroxy acid to use. It's called MCPBA, which stands for metachloropyroxybenzoic acid. So this benzene ring with the chlorine on it would be the R group for this molecule. When we add that peroxy acid, it creates an epoxide. So an epoxide is a 3-atom ring where one of the atoms is an oxygen. So we've seen this 3-atom ring in a couple of our mechanisms now. And then in our second step, we're going to add acid and water, so a hydronium mixture. So in our reaction, we can put these all together in one arrow so that it would look like this. And I'll switch over here after I get it drawn out. So instead of writing it separate, you would see it drawn out like this, where we have our peroxy acid on top of our arrow and that hydronium on the bottom. And if we were using MCPBA, we would just see that. We would see the MCPBA written above the arrow instead, or a specific type of peroxy acid. So we're going to look at the mechanism for this one. Now, part of this mechanism is going to look crazy and weird and new, and then part of it's going to look familiar to what we've seen. Here's the crazy part. So here's our peroxy acid. Now there is a lot happening, but we're going to focus on these 2 arrows because this is familiar to what we've seen. So just like our bromine reacted with our alkene, the oxygen's doing the same. So we're doing a nucleophilic attack on that oxygen, and then our electrons here are doing a nucleophilic attack back on that carbon. So these 2 arrows are showing the formation of that 3-atom ring. Now the rest of the arrows are kind of just doing electron flow. So these electrons are going over here to make a double bond between the carbon and the oxygen. And then this arrow is telling us that this bond is becoming a single bond and this oxygen is bonding to that hydrogen. So all of this over here is turning into this carboxylic acid. We don't care about it. It would end up in the waste. It is forming, doesn't really matter though. What we care about is that we just formed an epoxide. And so we're turning it on its side a little bit. We're using kind of a Hayworth projection just to see the 3D shape. And in that first step, we're going to add a proton to it. Now we know oxygen is not a good leaving group. We saw this in chapter 7. So we're doing a proton transfer to turn it into a little bit better of a leaving group. And so we're using our hydronium, because remember that was in our second step underneath that arrow. And then in our next step, we're going to do a nucleophilic attack. So we're going to take our water, we're going to do a nucleophilic attack on one of those carbons, and then we are going to open up that bond there. So we are breaking the bond between the oxygen and one of those carbons. Because we're using water as our nucleophile, we do need to remove that extra hydrogen. So we've seen this a couple times now. We're going to take off that hydrogen and break the bond to that oxygen. So we end up with one oxygen pointing up. This is the one that was part of the epoxide, and one oxygen pointing down. This is the one that added after the fact in that second step. And so we saw this same pattern with our oxymercuration reaction and our halogen reaction. One more, and then we'll do a couple practice problems. Now, it looks like there's more than one reaction on this page, but in reality, there's just a couple ways to do the same thing. So this is a Syn Dihydroxylation. So again, we're starting with an alkene, and we're going to add two alcohols, dihydroxyl, but we're going to add them syn to one another. So they're going to both be wedges or both be dashes. There's a couple different ways to do this. The first way is KMnO4, potassium permanganate, with water and hydroxide cold. So just meaning the temperature needs to be cold. The second way to do it is with OSO4, which is osmium tetraoxide, and then we would combine that with either NMO, which is over here, N-methylmorpholine N-oxide, or we could combine it with alkyl peroxide. And so here's an example of an alkyl peroxide. This portion is the peroxide, and then the alkyl just means there's carbon that's attached to it. So a common one to use is T-butyl hydroperoxide. And then in the second step, underneath the arrow, sodium hydrogen sulfite with water or sodium sulfite with water. So two different ways to do, well, a couple different, more than two, but a handful of different ways to do that Syn addition to our alkene. And we are dealing with manganese and osmium in this reaction. So again, two metals, and just like I mentioned with our mercury reaction, because it's going into the metals and the inorganics, it's not really mechanisms that we're going to pay attention to in this semester. So let's do a practice one with some of the reactions we've looked at so far. So we're going to start with our cyclohexene. We're going to react it with Cl2 with CH3OH, that is methanol. In another reaction, we're going to react it with MCPBA, and then in the second step, hydronium. And I have my arrow curving over here. We're going to react our third reaction with KMnO4, water, hydroxide under cold conditions. So in our first reaction, we are going to add our chlorine, and we're going to add the CH3O to our vinylic carbons. The chlorine is going to add to the less substituted side. So I know my chlorine is going to add there, and my OCH3 is going to add to the more substituted side. But to give it a little bit more information, we do know that the OCH3 and the Cl are going to add anti to each other. So I'm going to do a little erasing here. We're going to call that a wedge. We're going to call that a dash. So that puts them anti to each other. And then I need to put back in there that it started with. Now, in the examples that we saw on the slide, instead of methanol here, we used water, so we would have a chlorine and an OH group. But we can use alcohols as well, so instead of having an OH, we just have an OR group attached. Now, in addition to this, we would also make the enantiomer. So we're just switching all the wedges to dashes and dashes to dashes. With MCPBA, we know that we're making a dihydroxyl, and we know that it's going to be addition. So here is my ring, and I'm going to put my methyl on a wedge. It really doesn't matter what you do because it will form. So that means my alcohol here will be on a dash, which means my other alcohol will be on a wedge. And again, plus the enantiomer. And then on this one, we also know that it's going to be a dihydroxyl, but this one's going to be a syn addition. So I'm going to draw both of my alcohols on wedges, which means that that methyl group will be on a dash. And again, we can say plus the enantiomer. So similar reactions, but slightly different results. And then the last reaction we're going to look at in this chapter is called ozonolysis. And so I think that this is kind of a cool reaction because it is allowing us to completely change what type of functional group we have. So we're going from an alkene and we're going to react it with ozone in our first step. And in the second step, we have a couple choices. We can react it with DMS, which is called dimethyl sulfide. It looks like this. Or our other choice is to use zinc with water. And they're both going to do the same thing, so either will work. Now, what happens in this reaction is that our ozone is going to essentially cut our double bond in half. So I like to think of it as just cutting the double bond right here, and then we're just adding an oxygen to each of those carbons. So we end up with our 3-carbon chain right here. So here's our 3-carbon chain right here, and we have that double bonded oxygen. And then over here we have 1, 2, 3, 4. We have our 4-carbon chain with our double bonded oxygen. So the number of carbons stays the same. And what we're going to create are aldehydes or ketones. And just a reminder, a carbon double bonded to an oxygen is called a carbonyl. And if that is bonded to an R group and a hydrogen, we will get an aldehyde. And if it is bonded to 2 R groups, then we will get a ketone. So we have the possibility of getting either of those, and that's just going to depend on how substituted our alkene is. So the vinylic carbon on the left here had 2 carbons coming off of it, so we created a ketone for half of our molecule, and our vicinal carbon on the right has a hydrogen and 1 carbon group. I'm going to draw in my hydrogen here as well. So this one created an aldehyde. So it's definitely possible to make 2 aldehydes, 2 ketones, or a ketone and an aldehyde, depending on how your alkene is substituted. And we are going to do one more practice problem to end this, looking at the ozonolysis. And I do want to point out a lot of abbreviations in this video and in this chapter in general. And so definitely a good list to make for yourself. So I'm going to do 2 separate reactions. Okay, so I have my alkene and I'm going to react it with ozone, and I'm going to react it with DMS in that second step. We are looking at the mechanism for this one. It's a little bit more complicated than we need to get. So it is there. You want to see how it works, but this is how pretend it works. We just cut that molecule right in half. So I even like to draw it with the same. and then hydrogen here. And so we can double check our carbons. We had 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. We didn't lose anybody. We made one aldehyde and we made one ketone. So those would be our final products. Now those aren't drawn very pretty. We could redraw. There they are, drawn with a little bit nicer angles. And then in this last one, we're starting with a alkene that's in a ring, but the way we do it isn't any different. So there's where we're going to cut this. So if we think about this as one drawing, oh, let's see, I need to make my angles a little different here. That's essentially what we're doing. We're taking that double half and putting a carbon-oxygen double bond on either side. Now, of course, that doesn't look very nice. So what we can do, just kind of unravel it so that we end up instead of this weird thing. So 1, 4, 5, 6. I know it's hide, so I'm going to start with my. I'm also going to redraw it. So 1, 2, 3, 4, 5, 6. So we're making 2 aldehydes on the same chain because they were in a ring to start. So we opened up that ring, but we didn't break the structure up into 2 separate molecules. All right, that is it for part 3. There will be one more video for this chapter. Thank you.